LLMs can get brain rot. Abstract. We propose and test the LLM Brain Rot Hypothesis. Continual exposure to junk web text induces lasting cognitive decline in large language models, LLMs. To causally isolate data quality, we run controlled experiments on real Twitter/X corpora, constructing junk and reversely controlled datasets via two orthogonal operationalizations, M1 engagement degree and M2 semantic quality, with matched token scale and training operations across conditions. Contrary to the control group, continual pre-training of 4 LLMs on the junk dataset causes non-trivial declines. Hedges G greater than 0.3 on reasoning, long context understanding, safety, and inflating dark traits. For example, psychopathy, narcissism. The gradual mixtures of junk and control datasets also yield dose-response cognition decay. For example, under M1, ARC challenge with chain of thoughts drops 74.9 to 57.2, and ruler-CWE drops 84.4 to 52.3, as junk ratio rises from 0 to 100%. Error forensics reveal several key insights. First, we identify thought skipping as the primary lesion. Models increasingly truncate or skip reasoning chains, explaining most of the error growth. Second, partial but incomplete healing is observed. Scaling instruction tuning and clean data pre-training improve the declined cognition, yet cannot restore baseline capability, suggesting persistent representational drift rather than format mismatch. Finally, we discover that the popularity, a non-semantic metric, of a tweet is a better indicator of the brain rot effect than the length in N1. Together, the results provide significant, multi-perspective evidence that data quality is a causal driver of LLM capability decay, reframing curation for continual pre-training as training time safety problem and motivating routine cognitive health checks for deployed LLMs. Introduction. In 2024, the term brain rot was named the Oxford World of the Year when it drew increasing concern in modern society. Brain rot is defined as the deleterious effect on human cognition that comes from consuming large volumes of trivial and unchallenging online content or junk data due to internet addiction. The cognitive impact of internet addiction have been found to be significant along 3 dimensions. 1. Attentional capacities. The constant stream of online information often undermines the ability to sustain focus on reading articles or solving challenging problems. 2. Memory processes. The abundance of online information alters how individuals store, retrieve, and prioritize knowledge. And 3. Social cognition. Online interactions mimic real-world social dynamics, reshaping self-concepts and influencing self-esteem. Beyond for these cognitive impacts, a recent study in Turkish population found that internet addiction, mainly on X.com, is associated with higher psychological distress and changes in personality, including negative relationship with conscientiousness, extroversion, and agreeableness, as well as a significant positive relationship with neuroticism. In parallel to the rise of brain rot in human cognition, artificial intelligence, represented by large language models, grows to gain human-like cognition via learning from trillions of the very similar internet data. As a consequence of such a learning mechanism, LLMs inevitably and constantly consume enormous amounts of junk data like humans. Therefore, it is natural to ask if the analogous brain rot emerges in LLMs. Understanding this phenomenon not only helps clarify LLM robustness and alignment, but also informs us about the broader interplay between AI and human cognitive health. While LLMs obviously do not have gray matter or neurons in the same sense as humans, they do have parameters and attention mechanisms that might analogously be overfitted or distracted by certain data patterns. Prior work has identified data patterns that threaten LLM safety. For example, Chi and alumni demonstrated that fine-tuning LLMs on malicious or benign supervised tasks can void safety alignment. Compared to fine-tuning, pre-training could be affected more significantly, as LLMs have to continuously learn new knowledge from the uncurated internet data. For instance, LLMs can be taught to leak private information by poisoning pre-training data with crafted repetitive patterns. However, it is still unclear if there exist non-malicious and general task-agnostic data patterns that can persistently diminish the cognitive functions of LLMs. In this work, we translate insights from human cognition to LLM cognition by establishing the LLM Brain Rot Hypothesis. Continual pre-training on junk web text induces lasting cognitive decline in LLMs. To validate the hypothesis, we designed a controlled experiment that compares LLM behaviors after being fed with junk and control data. As outlined in Figure 1, we construct junk and control datasets from social media, Twitter/X, via the two junk metrics. M1, engagement degree, selects short but highly popular posts that often engage users longer online. And M2, semantic quality, flags content based on content styles that draw users' attention. Comparative benchmarking show that the junk intervention is associated with cognitive declines in reasoning. Comparative benchmarking shows that the junk intervention is associated with cognitive declines in reasoning, long context understanding, and ethical norms. We surprisingly find that some dark personalities of LLMs emerge with M1 junk intervention, casting significant safety concerns. Experiments on mixtures of junk and control data demonstrate gradual dose responses on reasoning and long context understanding. For example, under M1 intervention, ARC challenge with chain of thoughts drops 74.9 to 57.2, and ruler-CWE drops 84.4 to 52.3 as junk ratio rises from 0 to 100%. Our major contributions include threefold. 1. We proposed the LLM Brain Rot Hypothesis and validated it via controlled experiments. 2. Our detailed analysis uncovered fine-grained failure modes caused by junk intervention, including thought skipping in reasoning, and that popular data and short data contribute to different kinds of cognitive declines individually. And 3. We examined potential post hoc mitigation using similar scale of data, observing that instruction tuning is an effective strategy with more samples but cannot fully restore the cognitive capabilities. Such persistent brain rot effect calls for future research to carefully curate data to avoid cognitive damages in pre-training. Now I'm going to read a summary of the methodology that I crafted with Perplexity. So in this study, the authors wanted to test a simple but strong hypothesis. If you keep exposing a large language model to junk web text, its cognitive abilities will gradually deteriorate. They call this the LLM Brain Rot Hypothesis. To test this, they did not train models from scratch. Instead, they started from 4 existing pre-trained instruction-tuned models: Llama 3, 8 billion Instruct, Qwen 2.5, 7 billion Instruct, and Qwen 2.5, 0.5 billion Instruct, and Qwen 3, 4 billion Instruct. These serve as their baselines, representing reasonably capable models before any brain rot intervention. Next, they needed a clean way to construct junk versus control data. They used an old Twitter or X dataset with about 1 million public posts from 2010, where each tweet comes with metadata like retweets, likes, and replies. From this, they define junk and control in 2 independent ways. The first way, called M1, is purely engagement-based. Junk tweets that are very short but highly popular, high likes, high retweets, lots of replies, whereas control tweets are long and relatively unpopular. The second way, called M2, is semantic quality based. They asked a smaller model, GPT-4o Mini, to label tweets as high quality or junk based on content style and topic, using criteria like sensational clickbait, superficial lifestyle content, or conspiracy claims. High quality tweets become control, low quality become junk. A key design decision is that they balance the total token count for junk and control sets. In the engagement-based M1 setting, they only had about 1.22 million tokens worth of suitable control tweets. So they deliberately restricted the junk side to also be about 1.22 million tokens. That way, any differences in model behavior cannot be blamed on seeing more tokens, but instead on the type of tokens, junk versus control. They apply the same principle for the M2 semantic quality setting. With these 2 junk control axes in hand, they construct multiple training mixtures. For each metric, M1 and M2, they create blends with 0, 20, 50, 80, and 100% junk, always filling the rest with control data. So for example, in the M1 setting, a 50% mixture means half of the tokens are short, highly popular tweets, and half are long, low popularity tweets. This gives them a dose response ladder, from all control, through mixed regimes, up to all junk. Now, how do they actually apply this to the models? The training pipeline has 2 stages for every condition. Stage 1 is what they call continuing pre-training. Here, they take a baseline model and keep training it as a standard language model on one of those tweet mixtures, using next token prediction. All parameters are updated, there is no freezing. They use a small learning rate, AtomW, a co-site schedule, and train for 3 epochs over the synthetic tweet corpus, with BF16 precision and an effective batch size of 8. Functionally, you can think of this as extending the original pre-training on a carefully controlled slice of Twitter. Stage 2 is instruction tuning. After the continual pre-training step, they fine-tune the resulting model again on the Alpaca English instruction dataset with 5,000 examples. They do this for 3 epochs, again with a small learning rate and Adam W, and with a larger effective batch size of 16. Crucially, they also run this Alpaca instruction tuning pass on the original baseline model with no junk or control tweets. So all models are comparable. Every model has gone through the same instruction tuning procedure, but only some have been soaked in junk during the continual pre-training stage. Once they have these families of models, baseline, control only, continual pre-training, and various junk control mixtures, they evaluate them on a suite of benchmarks designed to probe different aspects of cognition. For reasoning, they use the ARC dataset, including an explicit let's think step-by-step chain of thought prompting variant. For long context retrieval and understanding, they use Ruler, which constrains synthetic context with needle in a haystack tasks, word extraction tasks, question answering, and variable tracking over sequences of up to 4,096 tokens. For ethical norms and safety, they use HH, RLHF, and Advanced Bench, and they derive risk scores by asking GPT-4o to rate how harmful or unsafe the model's responses are. Finally, for personality-like tendencies, they use the trait benchmark, which is built from psychometrically validated questionnaires covering the big 5 traits and 3 dark traits: psychopathy, Machiavellianism, and narcissism. To interpret the size of the effect, they do not only look at raw score differences, they compute effect sizes using Hedges G, which standardizes the difference between junk-trained and control-trained models across the 4 base architectures. A Hedges G above about 0.3 is treated as a non-trivial effect. This lets them say, for example, that junk exposure significantly harms reasoning and long context performance compared to control exposure across models. They also perform more fine-grained analyses. For example, they ablate the M1 metric into length-only and popularity-only conditions to see whether shortness or popularity contributes more to degradation. Separately, they hand GPT-4o Mini the chain of thought traces produced by the models on ARC and ask it to classify the failure mode: no thinking, no plan, skipped steps in the plan, wrong logic, or factual error. This reveals that most failures are associated with thought skipping, either no explicit reasoning at all or incomplete execution of a plan. Finally, they explore mitigation. They test training-free mitigation via reflective reasoning, where the model or an external model critiques its own wrong answers and then tries again. They also scale up instruction tuning and continual control training with more clean data. Even with substantially more instruction tuning data, in fact, several times more tokens than in the junk intervention, the damaged models do not fully return to the original baseline performance on reasoning, long context, or safety. This is where they argue that the brain rot effect looks persistent. Once the internal representation has drifted under junk exposure, standard post hoc tuning only partially heals it. That, in a nutshell, is their methodology. Start from capable instruction tune LLMs, carefully construct matched junk and control tweet corpora, continually pre-train on different junk control mixes, re-instruction tune all models, and then systematically measure how cognition, safety, and personality-like traits change as the dose of junk increases. And then I asked a few more questions from Perplexity to clarify. They don't say exactly how they feed. They talk about those batches, the batching, but they don't say exactly what that means. But one of the thoughts that I had was that just the shortness of text, so if you have very, very short tweets dealing with very different subjects concatenated together and being fed through the transformer, that alone could be potentially the source of this brain rot effect. And it doesn't make the study lose relevance because really, if you think about it, like the way these AI training pipelines work, there's a lot of automation involved. So just the shortness of content could have this effect, regardless of whether it's from Twitter or wherever else. If you're not careful when you're training pipeline, you could pollute your data. And this is probably not the only way that it can be done with Twitter. There's probably many other ways, like with Reddit comments and responses to Reddit threads and so on. So I found this fascinating, and the most important thing that I found fascinating was the fact that the models couldn't recover. So even after you tried to feed a tremendous amount of data back to the model to try to heal it, quote unquote, they weren't able to do it. Another thing that I found very interesting was that they had to actually trim the control data sets from Twitter because there's just so much more. Even though the tweets are short, the junk tweets are short, there's so much more garbage on Twitter than real content. Like everything is like a punchy, clickbaity headline instead of, actual thought. So I found that interesting that there's, even though the garbage tweets are shorter, the set of total tokens in garbage tweets is much larger than the control tweets. So yeah, I think this study is very interesting. So I wanted to summarize it, and I hope that I was informative, and I'll see you guys next time.